Welcome everyone. Today, as I mentioned, we have Michael Hahn. Michael is a Judy's undergraduate at Carnegie Mellon, and obtained his PhD at Columbia University, and he's currently an associate research scientist at Columbia. Michael is an expert in solid physics, observation, and also plasma physics, and he's also working on experiments. And today, Michael will tell us why the solar corona is so hot. Okay, Michael, take it away.
All right, thank you. Thanks for inviting me here to get to talk. I'm going to talk about Alfven wave damping and heating in the solar corona. And my focus is going to be, I'd like to tell you a little bit about a few of the current problems that we're working on related to this. Before I get started, I should acknowledge my collaborators. At Columbia, my longtime colleague Daniel and my group members, I had two postdocs who contributed to this project. Dusita worked on some of the atomic physics experiments that I'll mention a little bit about, and Shayak was working on our plasma physics experiments, and Stefan and Garima are the current postdocs in my group. Mabuba is a theorist who I've been working with on collaboration about looking at density fluctuations in the corona and their influence on Alfven waves. I'll tell you a little bit about that. Enrico and Elka have been collaborating on some of our observations. We do our plasma experiments with the group at UCLA and our atomic physics experiments with the group at Livermore. And also thanks to NASA, DOE, and NSF for supporting us. So you are, I suppose, all familiar with the coronal heating problem, but the basic idea, the photosphere of the sun, when you go outside and look at the sun, you see the photosphere, it is 6,000 degrees. The corona above it is 1,000,000 degrees, and the question is, how does the corona get to be 1,000,000 degrees? Why is it so hot? What is the non-thermal heating mechanism that brings energy from the photosphere into the corona? There are several major structures of the corona. There's the quiet sun, which are the looping magnetic fields, the quiescent loops of magnetic field. And then there are these coronal holes, which are the areas where the magnetic field stretches far off into interplanetary space. Those are the source of the fast solar wind. There are also these active regions above the sunspots. And the work that I'm going to talk about is most relevant to the quiet sun and the coronal holes. The active regions probably require additional processes to input energy. The basic idea of coronal heating is that everyone agrees that the energy source is the turbulent fluid motion in the outer convection zone. So there's mechanical energy in this fluid motion. And what this motion does is it jostles magnetic field lines around, and this transfers energy to the corona. One way it does that is by you can rearrange the magnetic field lines into stress configurations where they reconnect, releasing the energy stored in the fields. Or these motions in the photosphere can wiggle the magnetic field lines and excite waves that travel up into the corona, carrying energy with them. I'm going to focus on wave heating. Waves, we know, are found throughout the corona. In particular, I'm going to talk about Alfven waves, which are a wave where the magnetic field and the plasma are moving together. And these Alfven waves, if they are damped, then they can heat the plasma. So a problem has been to show whether or not they're damped close enough to the sun. If you just think about the effect of collisions, viscosity, and resistivity on the waves, they would get quite far away from the sun before damping, and so they wouldn't be an efficient heating mechanism. They would just carry the energy out into interplanetary space. So they need to be damped close to the sun, below about 2 solar radii. And then downward heat conduction will fill the corona with heat and create a sharp transition region. One of our major results has been to look at the amplitudes of these waves and show that they are in fact damped pretty close to the sun. So these measurements were made by looking at spectra of the sun and looking at the widths of the spectral lines. So the widths of the lines are broadened by the Doppler motions of the waves, so we can measure the wave amplitudes. This is the non-thermal velocity. This is essentially the wave amplitude as a function of distance. And the colored points here are our data, and then the solid curve is our average. So these are some different spectral lines. We measured the line shapes and inferred these amplitudes. If the waves are not damped, then since density is decreasing above the sun, the amplitude needs to increase in order that the waves carry the same amount of energy. And it turns out that the dependence should be like Alfven wave amplitude goes like density to the -1/4. So this dashed curve here is what you expect for energy-conserving waves. And we see that the amplitudes fall off of that curve somewhere between 1.1 and 1.2 solar radii. So we can estimate the energy they carry, and there's enough to heat the corona. And they're damped close to the sun. Other people have also been looking at this, and their observations support ours, so I think that people believe this now. So that leads to some of the coronal heating problems that I want to talk about today, which are, we're interested in knowing what causes the wave damping. I want to talk about reflection and turbulence and the possible influence of density fluctuations in the corona on promoting reflections and turbulence. Phase mixing, another wave damping mechanism. Phase mixing depends on the density structure of the corona, which we don't understand very well. So I'll talk about some atomic data to improve our knowledge of that. And then there are some properties of the waves that we don't know very well either, the perpendicular wave number or the exact Alfvenic wave mode. So I will talk about some ways in the future where we will try to measure what those are. So let me start with looking at reflection and turbulence and the influence of density fluctuations. There are density fluctuations in the corona. Part of them might come from acoustic waves, compressive waves, and part of it might just come from things that are erupting and going into the corona. So we would like to quantify these density fluctuations and then put them into a model in order to understand what is their influence on promoting Alfvenic turbulence in the corona. We looked at observations from SWAP. SWAP is on the Belgian satellite Proben 2, and it is an imager of the sun in 193 angstroms, so it looks at the extreme ultraviolet, and you see the corona here. And the nice thing about this imager is it has a very large field of view. The corners here go out to about 2 solar radii. So it does, of course, not just make images, it takes these images every 30 seconds or so, and so we get a movie. So we looked at 48 hours of data, and so in every pixel of this image, there is a time series for the intensity versus time. And I'm going to focus on this region looking below this coronal hole along the central meridian. This happens to be in an interplume region, which is a slightly less dense region of the coronal hole. The circles on this plot, the inner boundary represents the boundary within which we're able to do our analysis, and the outer boundary here is, I'll describe it in a minute. We use this to quantify the uncertainties or the noise from the detector. So we take these time series of intensities from all these pixels, and look, these intensities have fluctuations that depend on several things. The total RMS intensity fluctuation that we measure depends on the real fluctuations in the corona. This is what we want to measure. If we can measure the intensity fluctuations, we can infer the density fluctuations. But the measured fluctuations also include fluctuations due to counting statistics, detector noise, and real fluctuations from the solar disk. These are changes in the solar disk, brightenings and such that become reflected in the corona by the point spread function of the instrument. So we needed to account for all these different kinds of noise. The counting statistics we can do because we measure the average intensity and take the square root of the number of photons, and so we can subtract this off. To get the detector noise and the stray light noise, we use the corners of those images. So we assume that in those corners, there's no real emission, and all of the fluctuations in the corners are due to some kind of noise, and then we can subtract that off from the rest of our data. And so the result is that we measure the intensity fluctuations, and then from that we can get the density fluctuations. Now, the corona is an optically thin, collisionally excited plasma. So the intensity depends on the density squared. So there's one factor of density from the number of electrons and one factor of density from the number of ions. So that means that the relative density fluctuation, delta n over n, is half of the relative intensity fluctuation. So we take that, we find the intensity fluctuation, then we just divide by 2. And this is the density fluctuation versus height. And we can see that the density fluctuations grow quite large, like 10 or 20% density fluctuations at 1.3 solar radii. We couldn't go larger than this because that's where the noise was dominating everything. Even here, the error bars are large, but I think the trend is pretty good. There's 2 curves. There's a black and a red curve because when you're measuring a fluctuation, you have to pick what is the fluctuation relative to. So just to control for systematics, we looked at fluctuations relative to the previous 20 minutes of data, which we consider a running difference, and then compared to the average of the whole data set, just to see what difference it makes. And there are some minor differences close to the sun, but the basic trend is the same. So the story here is density fluctuations are increasing as you go away from the sun. And they seem to really start turning on between 1.1 and 1.2 solar radii, which is the same region where we saw our Alfven waves were starting to be damped. And so this makes us wonder, maybe these two things are related to one another. There is a couple of ways in which these can be related. One is particularly interesting in that the Alfven waves may be directly making density fluctuations. So there is a parametric instability of Alfven waves in which the pump Alfven wave, the outward going Alfven wave, couples to a density fluctuation in the plasma and generates two daughter Alfven waves, one that propagates outward and one that propagates inward. So it's a nonlinear three-way interaction. Shoda et al. In this MHD model, they predicted the density fluctuation amplitude due to parametric instability of Alfven waves. So here, they're on a logarithmic scale, and I was showing a linear scale, but the height range we're talking about is right in here. And you can see that a 10 or 20% density fluctuation is consistent with their predictions, depending on the value of this parameter, lambda naught. Lambda naught here is the, I think in turbulence we call this the perpendicular correlation length. I think if you're thinking of a wave, this is the perpendicular wavelength of the wave. And so you can see this perpendicular wavelength of the wave is basically the size of the antenna. I'll show when I show some experimental results later, you can see it clearly. But this quantity is uncertain to at least 4 orders of magnitude, which is why they considered 4 orders of magnitude of the value of this parameter, and probably it's even more uncertain than that, some people would say. So this is something that we would like to measure, this lambda naught. But anyway, parametric instability could be causing these density fluctuations. Even if the density fluctuations aren't there due to parametric instability, we still expect them to influence the Alfven waves. Alfven waves are expected to be reflected from these density fluctuations. So you mentioned these density fluctuations creating a kind of a corrugated plasma, and the Alfven waves are running into this. And those density fluctuations create a change in the refractive index of the plasma, which should cause reflection of the Alfven waves. And then the counterpropagating Alfven waves should generate turbulence. This is a model that I've been working on with Mabu as Gary Targey's model, and what we have been doing is collaborating to put observationally motivated density fluctuations into the model and see what their influence is on the Alfven wave turbulent heating rate. On the left is a smooth model. So this is a model with no density fluctuations, just a scale height change in the magnetic field and the density. The dashed curve here, this is heating rate versus distance, and the dashed curve is the heating rate required by the background atmosphere in this model. The solid curve, so you set up some background atmosphere, and then you flow Alfven waves through it and see how much turbulence generates heating. So the solid curve is how much heating can be generated by the Alfven waves in the model. So it's not enough in the smooth model. But if you put in density fluctuations at the level that we see in the observations, now here the blue curve is what's required by the atmosphere, and the black curve is what is provided by the waves, and now there's enough energy in the Alfven waves, enough reflection to cause the heating. So there's always enough energy in the outward going waves, but you have to reflect them efficiently enough to create this turbulent heating rate. So these density
we should think about the Alfven waves bouncing off of the turbulence? Is that off the density fluctuations?
Yeah, the idea is the Alfven waves are bouncing off these density fluctuations, and then it's the outward going and backward propagating Alfven waves that's to the turbulent gas.
Right.
So that's what's happening. Okay. That's one idea about what damps waves. Another is phase mixing, and this is something we're doing some experiments to look at, and so let me explain what this is. The solar magnetic field is organized into flux tubes. So if you look at the photosphere of the sun, there are these convection cells, and the convection pushes the magnetic field to the edge of the convection cells. Here's a magnetogram. These solid lines are showing the edges of the supergranules, which are the convection cells. And the grayscale is showing where the magnetic field is concentrated, white being positive, black being negative. So this forms the magnetic network. If you look at this from the side, what it looks like is in the photosphere, all the magnetic fields are concentrated in these small flux elements. As you go up into the atmosphere, the magnetic pressure dominates over the fluid pressure, and these flux tubes expand, and so they're bumping up against one another in the corona. Now, since transport is fast along the magnetic field and slow going across the magnetic field, these things can have different temperatures, densities, and magnetic field strength, so they can have different Alfven speeds. The Alfven speed is the phase speed of the wave, so the phase speed of the wave is varying in the cross field direction. It's just a kind of a cartoon of what it might look like in the corona. I think that the person who drew this had in mind in the interplanetary space, but you still kind of have this picture of all these little cells from these different magnetic flux tubes or magnetic funnels in the corona all bumping up against one another, and you have these Alfven waves flowing through that. The idea is that this can lead to phase mixing of the wave. What phase mixing does is it generates shorter perpendicular wavelengths. So the Alfven speed is the magnetic field strength divided by the square root of the density. Imagine we have a cylindrical plasma, and we're flowing Alfven waves through this cylindrical plasma, and we have a plasma that is higher density in the middle and lower density at the edges. So you put in a plain Alfven wave, and the edges are going to go faster than the middle, because the Alfven speed is faster in the edges. So these plane waves are going to become increasingly distorted as they propagate. So the Alfven waves on neighboring field lines become out of phase, and this generates to smaller perpendicular length scales, higher perpendicular wave numbers. So if you imagine taking a cut across the plasma here and looking at the magnetic field along that cut, close to the antenna, you would just have one peak. Further away, you get maybe two peaks in the magnetic field. Further away still, you have many little peaks in the magnetic field going across. So this is what we mean by higher K-perp. Higher perpendicular wave numbers lead to more rapid damping of the waves. They have a larger parallel electric field that couples them to particles more readily. So they damp more efficiently due to collisions and Landau damping.
Does it account to scatter it all the way to highest K-perp to be on the kinetic scale, or you're looking for slow dissipation of intermediate K-perp Alfven waves?
I don't think it needs to get all the way down to like a gyro radius to start increasing the damping rate of the waves, because you're changing the nature of the Alfven waves from a pure MHD, infinite perpendicular wavelength wave to one where you're thinking about kinetic theory anyway, and so you're getting that. So you can start having Landau damping. Normally, for the long wavelength Alfven waves, we don't think about Landau damping in the corona as being important, but if you start making larger K-perps, that can become more efficient.
Right, it's just that if I look at your plot, when you plotted the amplitude of the waves versus distance, it looked like the dissipation kicks in very compactly. So I would naively imagine that this is where the waves become kinetic and when the sort of dramatic dissipation starts. So I was just thinking.
Oh yeah, I know what you mean. So it could be. I think this would lead to a damping that goes like something like e to the minus distance cubed over some length scale, which could be something where it does seem like it turns on very rapidly like that. You're right. Maybe that's what's going on. Or in the reflection point of view, it could be that's the point where they get reflected. So we don't really know, but yeah. Anyway, so we wanted to look at phase mixing in the laboratory. We want to measure the rate at which these perpendicular wavelengths are generated and see whether it increases the damping in the laboratory. Just to understand the basic properties of Alfven waves and study this in a systematic way. So we did experiments at the large plasma device. It's a 20-meter long cylindrical device. There's many, the yellow and purple things are the magnetic field coils. You can vary the magnetic field in versatile ways. Here we just used a constant magnetic field. And there's two cathodes, one on the left and one on the right. And the one on the right side was a Lab 6 cathode, which makes a denser plasma than the barium oxide cathode on the right side. And it's a smaller cathode, so we could make a plasma that has a sort of a general background plasma and then a denser core. And so there's a gradient in the radial direction in this plasma. We have an antenna in the plasma at one side of the device, which we use to generate the Alfven waves. And then we put some probes at different distances away to measure the Alfven waves as they propagate away from the antenna in this inhomogeneous plasma. These probes are circles of wire, and so the time-varying magnetic field makes a voltage in them, and we can move them throughout the plasma. We pulse the experiment many times, it's very reproducible, and you build up a plane of measurement of the magnetic field. I'll show you one right now. This is the magnetic field in the plane of the device. These are the wave magnetic field vectors. This is in a cross-section of the device, and I'll play the movie, and you can see this is the Alfven wave. Oh, no. My own computer, it should work. There it goes. So you can see this is the Alfven wave. It's a torsional shear Alfven wave. And close to the antenna has this nice, basically cylindrically symmetric form. Now, as it propagates away from the antenna, so at the furthest distance of the probe, you can see the wave has gotten all messed up. Like there's lots of different current channels in there, and the generation of perpendicular wavelengths, shorter perpendicular wavelengths is obvious here. So we do see that phase mixing is happening, and we can look at this a little more quantitatively. So this is the evolution of the K-perf spectrum. So this is the wave power spectrum versus K-perf for no gradient is the gradient 0, some intermediate gradients, and then our largest gradient here is just gradient 3. So near the antenna, all of the waves have the same power spectrum as a function of K-perf because they all come from the same antenna. As you get further away from the antenna, the power spectrum spreads out, the energy goes to higher K-perfs, which is what phase mixing is supposed to do. And does that actually lead to increased wave damping? We see that it does. So this is the wave energy versus distance, and when there's a uniform plasma, the energy in the waves decreases a little bit, always because there's some collisions in this plasma. But when there is a inhomogeneous plasma with phase mixing happening, the decrease is much larger. So the basic story holds up, and what we are doing is we want to quantify this in terms of what is the initial perpendicular wavelength number of the waves we launch, what is the size of the gradient, and we'll be able to scale this to other situations and see how it applies to the sun. So this phase mixing depends on the transverse density structure of the corona, and we expect the corona to have transverse gradients in the density because it starts in these small fields in the photosphere. But we would like to actually measure what does that look like in the corona. But that's a very difficult measurement because it's an optically thin plasma and we're integrating along the line of sight. The best way that you could hope to quantify that is by measuring the emission measure differential in temperature and density, which is this mu of temperature and density. So mu represents the distribution of material along the line of sight in terms of its temperature and density. The way you measure this is we measure a bunch of different spectral lines with different atomic properties. And we integrate the intensity from each spectral line is an integral along the line of sight of, first of all, it depends on mu, the properties of the plasma, and it also depends on this contribution function G. G incorporates all of the atomic data that you need to know in order to interpret the spectrum. Ionization and recombination rates, collision rates, radiative transition rates, and all of these things. We know G pretty well as a function of temperature, but it is very uncertain as a function of density, and this is what actually prevents us from, you can make some inferences about the differential emission measure as a function of density, but they're very uncertain, and you can't actually measure mu and solve this inverse problem and find it because G is too uncertain. show you an example of this. This is from a paper by Peter Young, and so this is an active region, and this white line is showing the slit of a spectrometer across this active region. We measure the density. You measure a density using a spectroscopic density diagnostic, which is a ratio of two lines from the same element. So the idea is that and the same ion. By you taking such a ratio, you remove the temperature dependence, since the temperature dependence depends mostly on the ionization state. So he's measured the density as a function of, this is just a pixel number along this slit, based on an iron 12 and an iron 13 diagnostic. Iron 12 and iron 13 are formed at very similar temperatures. They should be looking at the same plasma. They should give you the same density. But we found that these densities were quite different. In fact, in some cases, they're a factor of 10 different. So that's a factor of 10 uncertainty in densities in our atomic data. So that is kind of bad. So we've been trying to do
Michael, the
Yes.
question was, what's the base of that logarithm? Is that base 10?
The base.
Yeah.
This is a base 10 logarithm. Yeah,
Thank you.
base 10 log of density. So yeah, 10 to the 9 per cubic centimeter is a typical coronal density, and active regions are a bit denser. Great. So we have been doing atomic physics experiments in order to calibrate these density diagnostics. So we've been using the electron beam ion trap at Lawrence Livermore. This is basically has a cylindrical geometry. There's an electron beam running down the axis of the trap, and there's also an axial magnetic field. Together, the axial electric field and magnetic field help to confine the ions in the radial direction. And then there are two biased electrodes which confine ions in the axial direction. We put ions into the trap. Electron-ion collisions occur within the beam, and then it emits spectra, which we can measure with spectrometers positioned outside the trap. And so from those spectrometers, we can control the density inside the trap mainly by varying the beam current. And so we can obtain empirical calibrations for these intensity ratios as a function of density. The points here are our results for some different experimental parameters. Beam energy shouldn't matter, but we always check systematics. And the curves here are flexible atomic code calculations for what these intensity ratios should be as a function of density. And in some cases, the theory does okay, and in other cases, we're off by a bit. So we are working on trying to modify these atomic calculations and see what needs to happen in order to better match the experiments, and in doing so, hopefully improve contribution function knowledge and be able to do a better job of interpreting spectra. One aspect of this that is kind of interesting is that EBIT spectra reflect the average density experienced by the ions along their path. And the ion orbits are much larger than the electron beam, and so they only spend a little bit of time in the beam. So one thing that we're working on is also interpreting the densities that we get out of the trap, because we really need to diagnose the spatial distribution of the ions, or the energy, which is equivalent to the energy distribution because it's an electrostatic trap. And so I am working on a model of calculating these ion trajectories for a large number of ions, and then comparing to the measurements and iteratively trying to back out the ion energy distribution. And then from that we can get a more accurate measurement of what is the density actually in the trap. There are also some uncertainties that depend on the detailed properties of the waves that I want to do. And so this is pointing the way towards some future observational work. So talked about the perpendicular wave number. It came up in two contexts. One is, what is this rate of phase mixing, or parametric instability, and also in the phase mixing rate. The phase mixing rate should depend on what is the initial perpendicular wave number of the waves, and how does it compare to the perpendicular gradient scale lengths. In the experiment, this length scale is obvious. This is the perpendicular wavelength. Okay, that's rough. You actually need to do some kind of a Fourier Bessel series, and then there's a spectrum of wavelengths, but okay, it's 20 centimeters in the experiment. But we have no idea what it is in the sun. This is the thing that was uncertain by 4 orders of magnitude in Shoda's model. So we would like to measure this perpendicular wavelength of the sun. Another issue that is sort of similar in terms of it's something that is just not spatially resolved in the sun is we don't know what is the exact form of the wave modes. There's two kind of wave modes that solar physicists call Alfven modes. There's the kink mode, which is really a fast mode, where the flux tube shifts side to side. And there's the torsional Alfven wave, which looks a bit more like the one in the experiment, where you have a twisting of the magnetic fields within the same magnetic flux surface. You can't distinguish these through measurements of the line width, and both modes are probably present in the corona. There are some indications of that. If you look at images of the corona, if you look at movies, you can see the kink modes. So imagine you take a line across an image of the corona. Here's the Alfven corona, and take this line at several different times in the movie and stack them up to make a time distance plot, and it will look something like this. So here's the position along this line, and the y-axis here is time, and so you can see the motions of things that are wiggling back and forth. So these are kink modes. So we know there are kink modes. It's very difficult to quantify exactly how many because due to the spatial resolution, you only see the ones that are large enough to cross a couple of pixels. So maybe there are more. We can also tell that there are probably torsional waves. If you look in the transition region and the chromosphere, you can see twisting structures. This is from a paper where they looked at the line profile of a magnesium-2 line in the chromosphere. So you take the intensity on the blue side and subtract the intensity on the red side, and you can tell whether you're seeing red shifts or blue shifts. And so here's an observation. This is looking down onto the solar disk. So you're seeing the chromosphere, and there's a lot of red stuff next to blue stuff, which implies that there's something moving towards you and something right next to it moving away, which implies a twisting structure. And these kind of twisting motions are the sort of thing that would lead to torsional Alfven waves in the corona. But again, we don't have a good quantification of how much, and this affects their damping. It also affects estimates of how much energy they carry, because the distribution of energy in the transverse direction depends on the wave mode. Our plan is to get measurements of these things using DKIST observations. So DKIST is a new 4-meter solar telescope dedicated to solar physics. It's a major observatory, billions of dollars, and it's going to be the next big thing in solar physics. And it has several instruments that are designed for high spatial resolution and high time resolution. So for example, there is the DL-NIRS instrument, diffraction limited near infrared spectral polarimeter. So it does polarimetry in addition to spectra. This instrument finds two-dimensional spectra. So it uses an array of fiber optics to take each pixel and turn it into a slit so that you can get the spectra from it. So we will have 0.03 arc-second spatial resolution, which is large compared to the images I've shown before are 1 arc-second spatial resolution. So this would be almost 100 times better, and cadences of 6 seconds. So this is we don't even really need 6 seconds. The waves probably have frequencies of a few minutes. So we will have enough time resolution to measure the waves and enough spatial resolution to look at the transverse profiles across the wave. So if you want to measure, for example, the perpendicular wavelength, we would want to look in the direction across where we see the oscillation and look at the coherence of the wave in that direction, and we will be able to do that. So I think that this is going to help us to better understand the properties of the waves in the corona and make better comparisons with theory and relate our experiments to the sun in a better way. So to summarize, observations support models of coronal heating by Alfven wave damping. I think that understanding the observed rapid damping and the heating of the corona remains a problem that requires collaboration between observation, laboratory, and theory. And I think that DKIST is going to provide us with novel, high cadence, high resolution observations that are going to provide important constraints on this problem. So thank you for your attention.
Thank you, Michael. Questions for Michael?
So in this phase mixing experiment, how?
Maybe
Probably want to get your mic for people on the.
In the phase mixing experiment, how collisional the plasma was?
I think there's about one, I have a backup slide somewhere that I can. Oh, I didn't put the collisionality on it. Okay, I think the ratio of the collision rate to the wave frequency is about 1. So.
Okay. The next question I was going to ask whether you can nail down the dissipation mechanism in the experiment. In reality, you would expect a competition probably between reconnection and Landau damping, because you were also seeing like strong current channels in the transverse plane. So if it would be collisionless, the Landau damping and reconnection would compete probably. But in the experiment, it's probably just dissipation in these current channels or something else.
We think we understand that the damping in the experiment is, in the case where you don't have the gradient, we can model the damping in the experiment very well just based on collisions.
Mm-hmm.
You can take the dispersion relation for the waves in kinetic theory, and we know the form of waves excited by the antenna, and you can just propagate that through the plasma, and it matches the measurements in terms of the damping rate due to collisions exactly. So when there's no phase mixing, it's definitely that zero gradient case where you saw the damping in the experiment, that is definitely due to collisions. In the case of what is it that causes the additional damping when you put the gradient in, we haven't tried to nail down what the exact mechanism is. We know that generating higher perpendicular wave numbers increases the damping rate, but beyond that, we haven't studied it yet.
Mordecai.
So let me follow up that question with a similar one. So I hear, from out of the field, I hear the claims from people promoting reconnection that there's enough energy there. I hear your groups and others claims that there's enough energy in the Alfven waves. Are they in fact the same order of magnitude? And just both mechanisms are actually contributing substantially, or do you have any perspective on that question?
I think the part of the problem with coronal heating is that there are a lot of things that provide a lot of energy to the corona. So it's almost not, it's not a problem of having some way to do it. We have too many ways to do it and trying to figure out which one is actually happening. In terms of whether you have Alfven waves or something like nanoflares where you're thinking of reconnection, there's the idea that these might really be the same thing, that Alfven wave turbulence, the dissipation might be through the formation of current sheets, which
that makes sense.
Sounds a lot like nanoflares. And so it could be we're talking about the same thing in a different way. Like there's the original Parker nanoflare model was about loops and you entwine the magnetic fields, but people sometimes take a broader view of what nanoflare means, and now they often use it to mean anything that causes an impulsive heating. So if you're willing to make nanoflares mean anything that causes impulsive heating, I think it could be Alfven wave turbulence.
Well, and Parker himself, Parker himself, of course, showed that very generally magnetic turbulence does end up in current sheets, and so in that sense, yes. Is that something you can address in the lab?
We have not succeeded in, so we have not, my group has not tried to make turbulence in the lab, but there are other groups who are trying to make Alfven wave turbulence in LAPD and in other places. In order to get the reflected waves in LAPD, we're trying to generate, to see naturally what happens by bouncing the waves off of a gradient or in an inhomogeneous plasma. In some way, they kind of cheat to make the Alfven wave turbulence by launching waves from two antennas towards each other. And they start to see nonlinear effects, but they haven't quite gotten into a regime where they see turbulence in the laboratory. But that is, there's a lot of interest in that, and they're working on it.
Very cool. Thanks.
Sasha and David.
Maybe a quick follow-up question. Like, your experiment, as you correctly mentioned, shows like a dissipation in a more or less uniform background. From observations, could you pin down sort of the level of strength of turbulence at that point where the abrupt dissipation happens?
Could you quantify the level of turbulence where the, yeah, I don't know of a way to do it. You could say we're going to look at the non-thermal broadening of the lines, which is like the turbulent broadening, but we've already said maybe the turbulent broadening is the wave, so it could be, how would you tell the difference between broadening due to a wave and due to turbulence? It's hard to tell.
I mean, in your experiment, you can pin down this. You measure the amplitude of the wave versus the background field that's much less than 1. So if you would have a measure of the turbulent component in B versus the guiding B, you could probably tell the difference. I agree with lines, it's probably very different.
Yeah, it's difficult to measure magnetic fields in the corona. This is one of the things that DKIS is trying to do with all these spectropolarimeters, is to measure magnetic fields in the corona. I'm not sure it will be, I mean, the methods have never been tried because it's been an ongoing, it's one of the big problems in observational solar physics is to measure the coronal magnetic field. And maybe they'll do a good enough job that you can measure magnetic field fluctuations. One thing that maybe is related is we've thought about trying to better quantify the shape of the spectral lines. So with the work that I've done so far, we've been using, like on Hinode, the instrumental broadening, the diffraction in the instrument is of the same order as the thermal and non-thermal broadening. With DKIS, partially because it has very good resolution and huge spectrometers, and also partially because it's looking in the infrared where the lines are much broader to begin with, the spectral resolution is much smaller than the expected line widths. So we'll be able to measure in more detail the shape of the lines. There are indications now, we've done some projects on looking at the shape of the lines, that they're not Gaussian, that they have broader tails, and they might be more consistent with like a kappa distribution. And then the question is this due to the distribution of the ion, the microscopic distribution of the ions, or due to turbulence? So turbulence, you expect to get some kind of a power law velocity distribution, which would create broad tails. So if we can measure several ions from different elements so that they have different masses, so that we can separate out what's due to fluid motions and what's due to the microscopic motions of each individual ion species, we might be able to quantify turbulence in this way by looking at how the shape of the line varies among the different species. So another DKIS project. We'll have to see if it works.
To go back to the beginning of your talk, you were looking at the fluctuations in terms of the variance, the fluctuations in the intensity.
Yeah.
And you got measurements of what effectively is sort of the 2-point function, right? Because it's the RMS fluctuations, a function of height.
Right.
I wonder if you have the information to look at effectively higher point statistics. You know, when you get to the level of 10 or 20% fluctuations, I suspect that the fluctuations could be non-Gaussian. And in some ways, you know, I can write that, say, now look at delta I cubed, measure delta I, you know, go look at higher moments. And in some ways, I think that may help distinguish between mode-mode coupling, which is only important, you know, which will dominate in the weak regime, and going to the fully nonlinear limit where you have, you know, dissipation on in filaments and things like that, sheets.
So you're talking about look at the statistical distribution of the fluctuations as a function
Yep.
of height. It's an interesting idea. Yeah, I'll look at it.
Michael, I have a question for you. So you talked about this mechanism of heating, and they all rely ultimately on the existence of turbulence and some level of magnetism. So these are probably very common features of stellar surfaces. And so I was wondering if you thought about extension of this idea of heating coronas around stars to other stellar types, and what that will imply for observation, for example, of higher energy emission from stars.
Yeah, so I haven't really done anything on other stars. I think that there are, the problem with the sun is that there are many different things that can lead to the heating of the corona. And it is probably true of other stars as well. So I wonder to what extent the sun is like other stars. It should be like some of them, but my understanding is that for a while people thought that the sun was typical, and now it seems like it's atypical in some ways in terms of the way its solar cycle and things like this. So so maybe it's Alfven waves for the sun and certain stars, and maybe it's nanoflares or reconnection for other stars. I think it would be interesting to try to figure out what is the regime of other stars that are similar enough to the sun where the same mechanisms can apply. I'd be interested in learning more about what kinds of observations you can make of other stars to try to constrain these parameters. I understand there's people who are trying to look at astrospheres. I don't think that's quite high enough resolution to really look at things. I mean, you've got some kind of, for other stars, from what I know, you have like the total X-ray flux or something like that, and that's the level of information we're at. And I don't know if that's enough constraint to say Alfven waves. Maybe if you have some model for what the star looks like, you could predict how many Alfven waves, and then you could say whether it's relevant or not. Anyway, I'm making things up because, I don't know, but it would be interesting to talk about.
Thanks. Any more questions? Okay. If not, let's thank Michael again. And yeah, thanks for joining. A lot of claps from Zoom. So yeah, thank you everyone.